Hello? Oh, hi. I'm Ren. I'm an engineer at Electric Capital. I work on this tool called codeslaw.app. It's used by security researchers and developers to effectively use like GitHub search across deployed contracts, which is a uniquely powerful aspect of a smart contract chain, such as Ethereum and L2s. Today I'll be doing a deep dive into L2 deployed contracts. A little bit different than some of the previous talks. A lot of hard work has gone into the Solidity community over the past, I guess it's been like 8 years now. And this will provide a very data-focused perspective on a lot of the hard work that has been done over the past few years. So a quick overview of the talk. I'm going to dive into the state of deployed contracts on L2s, backed up by our large indexing backend for codeslaw. And then I'll try and approach answering the question of, is there net new code on L2s, and how development patterns might be different on L2s compared to L1s, and hopefully show some interesting insights. So first off, taking a step back and looking at the landscape, the number of unique contracts by bytecode deployed by month has increased by 9x since 2021. A lot of that growth has been fueled on Ethereum, but over the past few months, especially in 2023, we see that about as many unique contracts have been deployed on L2s as on L1, which makes a market shift in the EVM and especially Ethereum ecosystem. And interestingly enough, there are now equally as many L2 deployers as there are mainnet deployers, showing the important prominence of L2s within today's Ethereum landscape. And another trend that we tend to see is that if you look at deployer addresses and you see which chains that they're deploying on, within the Ethereum ecosystem, we do see that starting from 2021, there are now over 120,000 deployer addresses who have deployed to more than one chain. Now some interesting insights. Anecdotally, we kind of have a sense that L2s might enable net new functionality that is very difficult and challenging to do on mainnet due to gas constraints, especially when the price of ETH goes up and in periods of high congestion. One of the interesting things that we see is that on L2s, transactions tend to consume 2 to 10x more gas than mainnet transactions. So for instance, the average transaction on Ethereum might be consuming between 200 to 300,000 gas. Meanwhile, on the L2s, we tend to see some numbers that are much closer to 1 million and well above 500,000 gas per transaction. One of the things when talking to Solidity developers on L1s is it's always about trying to cut back the number of events that you emit, because the more events that you emit, the more cost there is to the end user. This often leads to a lot of frustration from the data side, because, for example, if you're trying to do Dune queries or if you're trying to study user behavior on contracts, being able to have every single event tends to be a very challenging aspect. On L2s, because the cost to the end user tends to be a lot lower for emitting the incremental events, we do tend to see that L2 contracts tend to emit 2 to 5x more events per transaction than on mainnet. One consistent trend that we see in Ethereum, kind of like the Moore's law of Ethereum contracts, is generally cross-contract calls per transaction increases. This intuitively makes sense because as applications on Ethereum tend to become more and more complex in delivering more functionality to the end user, the functionality of contracts tends to be increasingly split from a single contract to multiple contracts. So you might have library contracts, storage contracts. But if we look at L2s, you can kind of barely see the trend on Ethereum anymore, because on L2s, L2 contracts tend to trigger more than 5x cross-contract calls per transaction than on mainnet. So now we get to the interesting question. So from the previous graphs, we already have a sense that potentially the behavior of developers on L2s it does seem that more gas is being used, more cross-contract calls are being used, more events are being used, which does suggest that potentially there is new functionality, new use cases that are being launched in L2s that previously would have been very, very difficult to do on mainnet. And there are a lot of ways to measure originality, but I'll approach it in three different ways, from easiest to most difficult. So the first is, if we just look at the method signatures that are used empirically, are they different on L2s? And then on the second, is the bytecode of deploy contracts different? And then the last, which is the most costly, but also potentially the most interesting, is if we generate embeddings from smart contracts, can we see noticeable differences between those embeddings? And I'll kind of dive deeper into what I mean by embeddings. So taking a look just simply at the method signatures, L2s only have roughly 25% overlap in contract functions called with Ethereum. And today, roughly 50% of the unique bytecode is deployed on L2s, which represents a market shift in Ethereum's ecosystem compared to 2021. And now to get into like the meat of the talk, one approach that we can do is we can study L2 code with embeddings. And this is very experimental, and a strong caveat I want to make is that this is an area of still very active academic research, with a lot of these methods still being developed today. And this approach is just one approach, but there are many others, and we're still really relatively early. So if we think about the problem of looking at a smart contract and then trying to answer the question, is this smart contract different than on an L2, different than a smart contract on L1, making that comparison in string form is extremely challenging. And we experimented with generating embeddings from smart contracts using CodeBERT to try to see if we could see differences in smart contracts in vector space. So a rough process of what that looks like is, first we dedupe the contracts by bytecode, because there also has been a rapid increase in proxy formats and factory patterns. We then tokenize the smart contracts, pass it into CodeBERT to generate fixed size vectors of a float 768 size. And then we can calculate the cosine similarities between the ecosystems and within each ecosystem. And then we can roughly normalize the differences by subtracting the within ecosystem mean similarity from the between ecosystem similarity scores. Some future research that we want to pursue in this direction is, one of the most valuable things about Solidity and having verified contracts is we will also be able to generate the ASTs and control flows, which will enable us to make much deeper explorations and stronger statements in this area. So a rough look of what this kind of looks like, you have Solidity code on the left-hand side, and then when you tokenize it and generate embeddings, you end up with kind of like a database of a lot of vectors. And when we compare the embeddings, we tend to see an interesting result. It's a little funny that this chart only has a few bars, but promise me, this took a lot of compute to generate. We kind of have two takeaways from this. One, Ethereum and L2s are less similar than their respective internal differences. And two, the L2s are more similar than their respective internal differences. And looking at the magnitude, we tend to see that Arbitrum and Optimism are more similar than Arbitrum and Ethereum, and Optimism and Ethereum are different. And this starts to suggest that there is net new code being generated on L2s. And I think my big takeaway from this is that Ethereum's L2 scaling approach is working. Solidity developers on the L2s are taking advantage of the lower gas fees. And interestingly enough, they're increasing gas usage by the same amount as the gas savings. So if you think about L2s as the end cost being passed to the user as being roughly between 10 to 100x cheaper than the cost of executing the same transaction on an L1. This is quite similar to what we see in Parkinson's law of bandwidth when you increase the amount of bandwidth that users in Web 2 have. YouTube and other sites tend to increase the quality of their videos, thus saturating the bandwidth. This indicates that there are likely higher compute use cases that exist on L2s that would have been challenging on L1, and this thus likely does create net new code. Thanks.
Thank you. Do we have any questions for Ren on L2 code? Yes.
Thanks. So you have showed that the distances, like how the distances kind of can be compared between L2s and like L1 and L2s. But like one of your conclusions was that people are taking advantage of like, again, bigger contracts and cheaper gas. However, this was kind of external to the research, right? I mean, it's not easy to check that this is exactly like what is different between the L1s and L2s, right?
Yeah, that's exactly right. This is one approach to check exactly what is the difference. I'm kind of triangulating on it through a lot of different charts. So for example, we see empirically higher gas usage, higher cross-contract calls, higher events, and then the initial LLM results does suggest that if you were to tokenize those contracts, there are differences, and the contracts on the L2s are more similar than the contracts from L2s versus L1. But to answer your question exactly, we have some further research that will come out in January where we'll be compiling all the contracts and generating the ASTs, control flows, which will provide potentially a deeper inspection there. And we also have a very large, like, sparse matrix of all the forms, all the events, all the ABIs, and additional fingerprinting and frequency analysis that might try and get exactly at what those differences are. We can also generate and see the differences in like opcode frequency and see if there are differences there. That research is coming in January.
Maybe you have to switch it on. Switch it on the mic. It's working, it's working. It is working, just speak.
This one's working. Hey, thanks for the talk. Did you also try to categorize the contracts being deployed? Like, did you see and then also, what caused those insane amounts of contract calls? Did you know what kind of contracts those were?
Yeah. We have some initial research on classifying the contracts by EIP. But in terms of being able to classify whether they're DeFi or NFT transactions or contracts at scale or teasing out the nuances there, it becomes a lot more challenging. I think one of the things that we have found is L2 contracts take a lot more liberal usage of storage in contracts. The most prominent examples of those today are like perpdex contracts. Those contracts then tend to use a lot of gas and tend to generate a lot of cross-contract calls because they're managing complex margin requirements that have to be stored across multiple contracts. For instance, on GMX, if you were to open or close a position, that transaction alone costs roughly like 2 million gas and fires off like 30 to 40 events.
Thanks.
Okay, there's another question here.
I have a question about the code word. You say you first tokenize the smart contract and then use the code word for obtaining the embedding, right? So there are some limitation about the length about in the code word, how to deal with the
Yeah. So most LLMs tend to have rather short context windows. The approach we used was we chunked the contract with overlapping windows, roughly half the size of the context width. This tends to be a common approach to provide greater context to the model. So that was the approach we took.
Okay. Thanks so much for the questions and for the great talk. Thank you, Ren.